Institute, okay, Istituto Italiano di Tecnologia Genova. That's actually in Italy. Okay, Italian language, fine. So the Normandy University, France. So he has completed his PhD in machine learning from IIT Bombay in 2015, receiving the Excellence in Thesis Award. He obtained his bachelor's and master's degree in computer science and engineering from the West Bengal University of Technology and Jadavpur University in 2008 and 2010, respectively. At IIT Bombay, Professor Banerjee leads deep learning in remote sensing and computer vision research group, currently comprising around 12 PhD students, several masters and bachelor students. The lab focuses on various aspects of deep learning in image and video analysis, including learning under limited supervision, multitask learning, visual language models, domain adaptation, generalization, lifelong learning across domains, multimodal learning, and visual. He has received several prestigious awards, including prestigious Young Investigators Award from IIT Bombay in 2021. He is also senior member of IEEE. He has published several papers in reputed journals and conferences, especially in top-tier venues in CVPR and several others, A-star conferences. So out of his all specific areas, I have requested him to deliver a topic which is really important, known as domain adaptation and all. So sir has agreed to give a talk on this. Thank you so much, sir, for accepting our request. Over to you, sir. Kindly unmute your mic.
Sure. Okay, thanks, Deepak, for the introduction, and thanks for the invitations. It's really a very important and very nice endeavor that you have, having this school on vision and kind of taking many, vision faculties all over the countries together. And it's really very nice initiative. Okay, so let me just share the screen quickly. Just a minute. Share the screen. Okay. I hope things are visible now.
Yeah, it's visible.
Yeah, okay. So let's go to full screen mode. Yeah, fine. So what I will do, I'll just talk about, the notion of this cross-domain learning, and basically there are two problems that we'll focus on. One is something called domain generalization, and there's another problem which is called generalized category discovery. Okay. And both of them, in some way or the other, involves the bigger notion of something we call open set learning. Okay. Which means, like, I mean, if in your training you have certain classes, but during testing if you have more classes, right, and this extra classes that we see during testing, so we don't have any prior knowledge about that. Okay, so that will be my main focus. So how we do this open set learning kind of a scenario for cross-domain task, and the two tasks that I'll consider is domain generalization and the category discovery. So I'll come to it and I'll discuss the problems and the solutions that we propose. So and this is some of our recent works, mostly published in the last 2 years. And for any query or anything, please stop me and I'll be happy to answer on that. Okay. Fine. So let's move. So basically, I'll just follow, this kind of path. So first, motivating why we need this DG problem. And as you know, nowadays, I mean, majority of the vision models, I mean, we use the VLMs because they have very good semantic, knowledge, because it's a vision as well as text modality that we want to align together. So it's semantically rich, right? And the way we interact with these models is through prompts, right? So we'll see what is prompt learning and I mean, how we use prompt learning in our scenario. And after that, like, I'll talk about three models. So basically prompt based ODG, then doing this ODG under very limited supervision. For example, if you have, say, one training example per class sort of thing. And then finally, I'll talk about how this class discovery thing, what is that, and what is our solution in this case. Okay. And then finally, I'll talk about some future directions and what is the takeaway from this direction of research. Okay, so I'll start from very beginning. So when we talk about supervised learning, and then you know that I have a space of data, which is X, and the space of labels, which is Y basically. And I have samples, this X, I, Y, I, which are, of course, sampled from some unknown distribution P. And we typically assume that all the samples are basically IID, identically and independently distributed. Okay, so that, I mean, there is no bias in the data set, and you can actually think of making a classifier which should work well on new data, which are the test data, I mean, which are like disjoint from the training data out there. And our goal is to model this hypothesis F, which comes from a bigger hypothesis space. And what I want to do, how do I, fix this hypothesis? I mean, on the training data, basically, I have a measure of disagreement between what the model produced, so this F of X, and the ground truth, and I define some loss function, right? And typically, if it is a classification problem, so it's cross entropy loss. If it is regression problem, it's an MAC loss. Now, this whole setup, apart from this IID assumption, it has another very important assumption, okay, for this model to work properly on this test data, which says that the training and test data, they should come from the same underlying distribution P, which means, like, if your training data, for example, are the color images of cat and dog, and then your test data should also be color images of cat and dog, right? On the other hand, it may happen that your training data are the color images of cat and dog, but during testing you may have sketches of cat and dog, right? So in which case, of course, the visual style of your color image and sketch are very different, right? In which case we say that the training and test data are not coming from the same underlying distribution out there, and we are interested in this specific scenario. Okay, so because when you apply this machine learning model in real life, you can never expect that the distribution governing the training data and test data are always going to be identical. It never happens. For example, you have a model, I mean, for example, which you have trained on data collected in a sunny condition, right? Now you want to apply the model in the rainy or snowy kind of condition out there, right? And this is clear. I mean, of course, the style, the visualizations of the image will differ drastically from the normal sunny day and the rainy or the snowy day out there. Okay. Now, this kind of ambiguities, or this kind of differences in the training and test data are cannot be handled by standard supervised classifiers. We need to do something, specific to handle this kind of a scenario. Now, and here comes the notion of learning across domains. Okay, and when we say this learning across domains, again, just to be on the same page, so I want to make a model which can be trained on one domain or one style of data, and that should be applied during testing on different style of data. Okay, so that's, I mean, in very simple sentence, the problem that we want to solve. Now, I mean, this can be solved in two ways, either through domain adaptation or it could be through domain generalization. Okay. So when I say domain adaptation, so here is a setup. I have a labeled training data, which typically we call a source domain, and let's assume that the data has come from some distribution PS. Now I have some unlabeled test data, which we call the target domain, and it has come from some other distribution, say PT. So very importantly, PS is not equals to PT. They are two different type of information that we have. So PS could be color images and with labels, of course, and PT could be sketches, for example. Okay. Now, given this situation, what I want to do, my goal is to make a class. And remember, this information, both the source data and target data, are jointly available in domain adaptation. Okay, it's not that the target data, the test data that will come during inference is not like that. If it is domain adaptation, both the information should be available together during training. Now, given this data together, so it's basically some sort of transductive learning that we do, right? In this setup, basically, I mean, our goal is to make a classifier with respect to the source data set that should work equally well on the target data. Okay, so that's why if you see the loss function, my goal is to optimize the performance on this target data. So any XY coming from PT, but I can only make a classifier based on the source data, right? Because there I have the labels only. So that's domain adaptation. So if I put the visualization, you can see that. So maybe the top one could be and if I represent, if the data is labeled, so it's a solid kind of either rectangle, star, or circle. If the data is unlabeled, then it's not solid. Okay, so there is no color inside, right? So you may consider the top circle represent the source data, where each shape defines a particular level of the data, and in the below one that represent the target domain. And of course, since we do not have any labels, so that's why we are not putting any solid kind of color out there. When I do domain adaptation, what is the goal? The goal is that I want to learn a embedding space, of course, which is abstract, where the data from the same class. Okay, because remember that in target domain we don't have the class information, right? Although I assume that uh, that is a closed setting. If there is cat and dog and tiger in the source domain, I'll have sketches from the same set of categories only in the target domain, but I don't know the exact label for each image in the target domain. Okay, so what is my goal? I want to learn an embedding space where basically data from same class, irrespective of the domain, should come close to each other, so that the classifier that you can learn with respect to the source data can be used to classify any target domain sample. Okay, so that's the problem definition. Now, this domain adaptation has this inherent requirement that the target domain basically should be available during training. So whatever objective I do in domain adaptation, so that involves both the source domain and target domain together. Okay, so all the loss function should take data from both the domains, which may be a restriction in many cases, because we may not have access to the target data during training, right? So to come, to have a solution for this situation where the target domain may not be available during training. And one example could be, let's assume there's a robot and you have trained a robot to recognize again, say, cat and dog. Okay, now the robot moves in different rooms, different environments, and we don't have any idea about the environment, right? So in each room the illumination, the lightning would be different, right? And again, each room is a new domain here, right? Because of changes lighting, the the alignment or the configuration of the room, given all those ambiguities, it's a different distribution of data. So now, I mean, in these situations, of course, there is a possibility that we may not have access of the target data during training time. So what do I do in that case? So in domain generalization, the plan is that, so here instead of one source domain, I have access to multiple source domains. So here you can see that in this figure. So I have three source domains, okay? And let's assume that I have the color images, the cartoon and painting of cat and dog, okay? The two categories. Given these three domains, my goal is to make a classifier. Given all the three domain knowledge, and all the three domains are labeled, it's called multi-source domain generalization, basically. Okay, because we have data coming from multiple source domains. So given this three different source domains, my goal is to make a domain invariant classifier system, so that during testing, any target domain, any unlabeled target domain might come up, but the model should be able to do proper classification of this target domain data. Okay, so that's domain generalization. So I hope the difference is clear now. So in domain adaptation, again, we have a single source and single target domain. The source domain is labeled, but the target domain is unlabeled. So my goal is to learn a feature space where the samples from both the domains should be class-wise aligned, so that the classifier that you train on the source data should be applied on the target samples. Now, when I do domain generalization, I have multiple source domains. Of course, each source domain has different distribution, but of course, all the source domains are labeled, right? So given this labeled source domains, I want to train a classifier, so that this classifier can handle any target domain that will come during testing and will do proper classification. Okay, so that's the two problem. So basically, as you can understand, that this domain generalization is more practical than domain adaptation, right? Because domain adaptation you can apply in very specific scenarios where you already have the access of the target data, but domain generalization is is the model that we want, right? So basically, whatever model that we want to deploy in real world, so I want the model to be domain generalizable, right? So it can take any distribution of data, any style of data during testing, and it should be able to do proper classification. Okay. Now, of course, there are some other technical, differences as well. For example, if you see the third point, since our domain generalization model is trained on multiple no, so domain generalization is not self-supervised learning. Okay, so in self-supervised learning, basically what you want to do, you want to learn some representation only from the data, right? So both DA and DG are supervised setup because in the source domain you have labels. Okay, basically you're solving a classification problem, supervised learning problem, but in self-supervision you don't have access to any sort of labels, and what you want to do, you want to just exploit the data only to learn a good initialized feature that could be used to transfer to any other task out there. Okay. So, I mean, the point that you're telling in DG, since I mean, you have multiple source distributions available during training. So basically, it has less overfitting issue. Okay, because I mean, the model already it has seen diverse types of data, so it can handle the overfitting in a much better way. So that itself gives some regularization to the model actually. Fine. So given this importance of DG, so I'm going to focus on this domain generalization in the rest of the talk. Fine. Now let's extend the problem a little bit more. So as I mentioned, the DG problem. So again, it has k different source domains, and each source domain again is labeled, and they have data from some known set of classes. Okay, you can assume that in each of the source domains, one could be say painting, and the other could be color image, and the third one could be say cartoon. But you have labeled data of cat and dog only. Fine, that's the training data that we have. But now, and let's assume that I make a domain generic classifier, blah blah, all sort of thing. Now let's assume a target domain Q comes. But in the previous definition, it was a closed set kind of setting that I mentioned, right? So I assume that in the target domain also, I will have data coming from a new distribution, but the images in the target domain will be from one of the classes. Okay, it may be say a clip art domain, but it could be of image. The images could be of cat and dog only. Okay, so it was a closed set setup. But now let us relax the problem a little bit more. So now I am telling that in the target domain, since of course the target domain is unlabeled and unrestricted, right? So I don't have any access to the target data. So I cannot assume that it only has data from the known classes only. Okay. So now what I'm saying that the target domain will have data either from the known classes or from completely new classes. Okay, so now the label space of my target domain is Y, which is the set of known classes, and there could be new classes, and combiningly I'm telling all these new classes to belong to this class level called unknown. Okay, now given this situation, what I need to do, what I want my classifier to do, I want any sample from this queue to be classified as in one of the known classes if actually it belongs to the known class. If it does not belongs to any of the known classes, then the model should output unknown. Okay, that's what I want. Basically, if I have say C classes in total, C known classes in total, I want to make a C plus one class classifier. Okay, where the first C indices they correspond to the known classes, and the C plus one index that corresponds to the generic unknown class out there. Okay, so let me go through it once more. I have K labeled source domains, and let's assume this capital Y defines the level set. I want to make a domain generalized classifier. Now during testing, a new domain Q is coming. But now Q does not only have samples from the known classes only, but it may have samples from some completely unknown classes. And what I want my classifier to do, the classifier should classify any potential known class sample to one of these Y categories. If it is unknown, that it should give a reject unknown whatever separate label for this new samples out there. Okay, and as you can understand, this problem is much more real world oriented, right? Because here we actually can because the real world is very dynamic, right? So we cannot put any assumption on the target data that it will always have known classes. For example, you have a model for to detect all the surroundings for a driverless car, right? And the car is moving, so in the daytime, evening time, night time, and all. So in night time, quite, or the evening time, it may be quite possible that the camera in the car, it detects some new type of, pedestrian, a new type of other object, right? So what it should do with respect to that, because in the training it may not have encountered those particular type of object, right? Then it should say it's an unknown class or it's a no-fault class, right? So that is what we want to do. So by the way, is the problem clear, the ODG? Anybody, any question till now? Okay, so if the problem is clear, so let's have the solution for that. Okay, now let's divert our discussion a bit. Nowadays, this VLMs are pretty popular, right? Because previously, the way we used to solve the problem was, we used to make a something like a CNN based or VIT based classifier. Probably we should put some regularization that should ensure that the model should handle multi-domain data properly, or you just put some extra loss function so that this alignment across the domains, those kind of thing can be done in a better way. Okay, for that matter, like when you put this batch dom layer in your network, so that has some domain alignment effect actually. Okay, so that's why in many of these models there is the variations of batch dom, or rather this learnable normalization, they have been used quite drastically. Okay, of course there are other models where basically we put some extra loss function, that one loss function could be entropy loss, right? So what you do, you pass that, you train a classifier on the source data, and you pass the target data, pass through the same classifier, and you minimize the entropy. Okay, so then what it will do, it will make sure that the target data belongs to one class with high probability and all other classes with low probability. Okay, so this kind of simple thing could be done, for the alignment kind of purpose out there. So finally, as you can understand, this is more of an alignment problem. So you have to learn features which are domain generic, so that in the feature space, in the latent space, all the domains can be aligned properly, so that whatever classifier you can make out of the source data can be applied to the target domain sample. So that's basically the idea. Now, since already CNN or VIT models trained solely on the vision data, they don't have the semantic ideation, right? So by semantic, what do I mean? Whatever we represent in terms of language, that is a semantically rich content, right? But on the other hand, visual models, so they are not that much semantically rich, because there is no kind of language information, that has been encoded in those models. So that's why, like, you could use ResNet 101, VITB16 and all sort of model, but still they have some limitation because of this language barrier out there. With this VLM, the Vision Language Model, the foundation model, what happened? We trained this model with respect to both vision and language modalities together, right? And that's a good thing. So now we have reduced the semantic gap of these models to a great extent, because now we have a model where there are two encoders, right? One to encode the image and the other to encode the text. And what is the text in this case? The text is basically some representation or some description of the image out there. Okay, so now when you align this, both the pieces of information in some common latent space, so the space becomes very rich, semantically very rich. So that's why, these models have shown huge performance improvement for all this classification, recognition task, and to some extent to the cross-domain task also, right? If you want to do domain generalization, adaptation, those kind of tasks with this VLM as your backbone, the model has shown huge improvement compared to only vision backbone based methods which are out there. Okay, and among this, vision language model, so the CLEAP, this model is very popular. Okay, and CLEAP is a model which has come up from OpenAI, the same company from which this GPT model has come up, this Chat GPT and all. So this CLEAP is extremely powerful model out there. So CLEAP, basically the way we interact with CLEAP is through prompting. So you pass the image through the image encoder, and the textual information, the textual query or whatsoever we want to pass, that is through something called prompt. It's basically a description, but let's call it prompt. And this model shows very good zero shot performance, and it can handle multi-domain data in a better way. So there are some good things about this model out there. And this model has been trained on a really huge volume of data, almost 400 million image text pair curated from the internet. So that's why it has seen enough variation, okay, so that it can do better zero shot adaptability, or it can do better generalization, those sort of things. Okay, so this is a representation of clip. So basically, I have set of images. I pass through the image encoder. I have the, let's call it prompt from now on. I have the prompt. I pass through a text encoder. And then what I do, I want to project them in a common space. And the way I train is very simple. It's a contrastive loss, right? So basically, I want to bring the correct image and text embeddings close to each other, and incorrect image and text embeddings far away from each other. That's a simple thing. But the only point is that it has been trained on at least 4 million image text pairs. It's a huge volume of data. The model has seen enough variation. Okay. Now, so this is exactly what I just mentioned, right? So this if image is the image encoder, so it project any image into this d-dimensional feature space. If text is the text encoder, that project the data into some d-dimensional feature space. And then this is my contrastive loss. I want to bring the image to the correct text and take it away from all incorrect text. So basically, it does a two-way training, where in one part of the loss. So in the first part, as you can see, that the image is the anchor and the text is either positive or negative. In the second part, the text is the anchor, where given a text, I want to align correctly with the correct image, and I want to take it away from all incorrect image embeddings out there, right? So it's a two-way loss. In one case, the image is the what you call the anchor, and in the other case, the text is the anchor. Okay, and once you train this model with respect to this simple loss, during testing for zero shot, what you can do, you just take an image, you get the image embedding, you take the set of classes, you get the text embedding, and you just evaluate the cosine similarity between them. And wherever you get the highest cosine similarity, so the arc max, so you say that the image belongs to that class directly. Okay. Now, given this simple, phenomena, and this is extremely good, extremely powerful. Okay. Now, what happens? Everything in Clip depends upon the quality of the textual information that we are giving. Okay. So in standard classification, what do we do? So in standard classification, it's a class name, right? And you encode the class name in terms of one odd vector, and then you try to assign one of this vector representation to the input image, right? So that's the mapping that we learned. But here, as is a two-way process, and the class name also should go through the text encoder. Instead of just saying the class name only, cat, dog, rather I try to put a sentence. Okay. And the most popular sentence to define the class name in Clip kind of model is this: a photo of a cat, a photo of a class, basically. Okay. Where in place of class, you just plug in the whatever class name that you have. So basically, what you do through the text encoder, you just pass this prompt: a photo of a cat, a photo of a dog, this kind of thing. And through the image encoder, you pass the respective images, and then you do this contrastive loss during training, or this cosine evaluation during testing. Okay, so that's the how Clip works basically. Fine. So now the question comes. Okay, by the way, so this photo of a cat or photo of a class for that matter is a very generic prompt, right? So ideally, in multi-domain setup, okay, by the way, so let me just talk about some multi-domain datasets which are available. For example, domain net is one dataset. Okay, then another dataset is called PAX. Another dataset is called Office Home. If you see those data, for example, in domain net, you will see that there also, let's say PAX. Okay, so PAX basically means photo for P, art for A, cartoon for C, sketch for S. Okay, so that's why this packs. If you see that within this data set, within the main folder, you will see 4 different folders. Okay, so these 4 different domains, and within the each domain, you will see that there are 7 folders, which basically each domain has data from 7 classes. Okay, so the number of classes are 7. You'll see whatever classes are there, but for each class, you have data coming from one of these 4 domains. Okay, basically from all the 4 domains out there. So, in those cases, instead of putting a photo of a cat, it may be more meaningful if you directly use the domain information in the prompt, right? For example, if I'm handling a cartoon, I may want to have the prompt as a cartoon of a class, or a sketch of a class, or thermal image of a class, right? So if I put this domain information directly, then clip is found to work better, right? Because I mean, a cartoon of a cat is a more directed kind of prompt than simply putting a photo of a cat. Okay, so that's the main difference. Okay, so that's why, like, I mean, if you're dealing with multi-domain problems, then typically I'm trying to put, like, based on the image that I'm handling currently, I try to put a prompt which has this domain knowledge. Okay, then it has found to work better. Well, this is good, but in either of our setup, whether it is domain adaptation or domain generalization, it's not easy to know the domain name for the target domains, right? Because remember that the target domain in both the cases, be it domain adaptation or generalization, in both the cases the target domain is unknown, right? We don't know what it, because it's unlabeled and unknown ideally. Okay, so since we don't know the target domain, so I cannot just for the target domain images, I cannot define the prompt, right? Because I don't know the target domain. Okay, so that's a problem out here. So that is why it has been found that this notion of what you call manual prompting, although it works well, like if you have all the knowledge, all the information available, but when you apply in real world, this manual prompting thing is not going to help you much. Okay, so what we can do instead, we can actually come up with an idea called prompt learning. Okay, so these two papers, this one is called co-op, and the other is called co-op. Okay, so the first one is called context optimization co-op, and the second one is called conditional context optimization co-op. So these become extremely powerful because they introduce the idea of prompt learning. Let's see what they are. See, like each of these words in the prompt, like for example, the a photo of a class. So how many words are there? A photo of a. There are four basically what you call the prefix, the context tokens, and then I have the class token out there, right? So, and how do we define them for in a computer and machine learning model? So I have an embedding corresponding to every word, right? And it could be a BART embedding, word to fake embedding, whatever. So basically, for a computer, it's actually a vector of size 5, and each vector has a fixed dimension. Okay, that is the dimension of your what to fake or BART, what kind of a model. Now, in prompt learning, what I do, by the way, I mean, once I train Clip, the Clip model is frozen. Okay, so I don't do anything on the Clip backbones, right? So, I mean, the way I can interact with Clip is by, having a better prompt out there, right? So, yeah, I mean, so there's something called parameter efficient fine tuning, I mean, which is pretty common in this large foundation model, be it LLM or VLM whatsoever. So, basically, I mean, the thumb rule is that you cannot, fine tune the parameters of the model, right? Because that will have a very high forgetting effect. Instead, what you do, you just try to tune the input to the model out there. For example, in which case we do prompting or prompt learning, or you just put an adapter, okay, which is a parallel networks where you just try to learn extra thing that you want to add to the actual network content. Or you can do something like a parameter efficient fine tuning, something, for example, there's something called LoRa, low rank this optimization, okay, where you are trying to add what extra thing that I can add with the current content of the network. Okay, these are the things that we typically do, and here basically we are trying to interact with the Clip model by learning the prompt out there. Okay, so what I do, since I know, for example, that there can be four context tokens, like the a photo of right? So there's four words, and let's assume that I want a sentence of length 4 plus one token, one word for the class name. So this prefix tokens, let's assume that is 4. So what I do, I define 4 random vectors initially, that should correspond to the 4 weight, and then I make the prompt by concatenating the class token with that, right? So this is the total prompt right now. And what I do with respect to the contrastive loss that I have on this downstream data, of course, I just make these vectors learnable. So basically, what does it mean? What I want, given this, so you have a frozen Clip model. Now I want to adapt Clip for some downstream data. Then what I'm going to do, I'm going to pass the image fine on the frozen Clip vision encoder. Now for the text, what I'm doing, I want to learn the optimum prompt. So I just make the prompts learnable. Okay, which means the context tokens, the initial photo of, like this kind of words, I just want to make them learnable. And with respect to the final, this image text contrastive loss, whichever is there, but my Clip models, both the text encoder and image encoder, they're frozen. Okay, I am not touching them at all. So this is what is called prompt learning. Okay, as you can see, like, I mean, of course, like, I mean, you don't have a clear meaning of what this v1, v2, v3, vm they're learning. I mean, it could be something abstract, but it has been seen that this kind of prompt learning is better than doing this manual prompting. Okay, so that's the next concept. So that was co-op paper, which became extremely popular. It came up in 2022, and then what they found, it has a one problem, which is that so basically for every class, I mean, there could be many images, right? But of course, there will be a single prompt for that class, right? Or prompt template. Then they said that, okay, so basically this was co-op again. So your this context tokens are learnable, and the class token could be one of the classes. Your text encoder and image encoder are frozen. You pass the image because this is on the downstream data, right? And then what you want to do, you just try to learn the prompt with respect to the contrastive loss between image and text embeddings. Now, next, what I mentioned that in co-op, I mean, for each class, finally we'll end up having a single prompt, so that we have some overfitting, because I mean, it's not easy to map many images to a single prompt out there, right? Then what they do, I mean, in the prompt, they try to add the image information directly. So it's a pretty interesting idea. Again, I have this v1 to vm, the learnable prompt. I pass them through the text encoder. I have the image, I pass through the image encoder. I guess get this image embedding. But the image feature, I want to add to each of the prompt tokens through some meta network. So this meta net is basically some fully connected layer. Okay. So basically, I want to project some transformation of the image feature also into the prompt. So now basically, this is the idea of image condition prompting. So now what you will have, so the prompt tokens are common, of course, the context tokens, so that will remain unchanged. But since you are adding the image information, so basically now you have per image prompt out there. Okay. So now when you have an image, you have an prompt for that image. Okay, so that's a pretty interesting idea. So now if there are 10 images, basically you'll have 10 prompts. Okay, for that for each of the images out there. And then, and typically this is how we do it, and this meta net is a fully connected layer, so that let's assume that the image encoder gives 768 dimensional output, and then through a fully connected layer, you just convert to whatever dimension should be there for the context token for each word out there. Okay, and you just process it. So these two papers become extremely powerful, and because I mean, this is how you just fine tune and VLM for a downstream data, and you are not doing manual prompting, rather you're doing prompt learning. Great. Now, there's another concept I want to bring in. I mean, in co-op and co-op, what happens? I'm only prompting the text encoder, right? So basically, I'm just adding this learnable prompt in the text encoder, which is not kind of exploiting the synergy between the text and image encoder, because Clip is not a single model, right? Clip has both image encoder and text encoder, but this kind of prompting of what co-op or co-op does, it's called unimodal prompting, because I'm only prompting the text encoder. So then there's another paper came up in 23. It's called Maple, and it introduced the idea of what we call multimodal prompting. So if you see the photo here, I mean, because the top photo is for the co-op, where you learn the prompt for the text modality only, the text encoder. But now what I'm doing, I'm trying to learn some prompt both in the text and the image encoder. Okay, and that has found to do better generalization. Okay, and that's the paper Maple, and that of course, like kind of outperform the performance of both co-op and co-op out there. Okay, so that's the next kind of direction. So basically, when you use these Clip models, you can either do unimodal prompting or you can do multimodal prompting, and of course multimodal prompting is better. Well, again, uh, so first, what I mentioned, that a manual prompting is not good for domain generalization tasks, because for the target domain, I may not know the exact domain name. Then my solution was, okay, let's do prompt learning. Okay, so I can do either co-op, co-op, maple, any of these methods. But this models, they are found, I mean, that they have issue in handling the cases where the source and target domains are extremely different. Okay, for example, if your source domain is sketch or cartoon sketch and your target domain is clipart, for example. Okay, so then these models have huge problem in dealing with that. And so that's the one issue, one sort of issue. And secondly, I haven't talked about how this model can handle any unseen class, novel class sample during testing, right? The open set scenario. So it is found that this co-op, co-op, maple, all these techniques are basically designed for the closed set. Okay, so they don't have any idea to handle the open set out there. Okay, so now what we're going to do, so this is basically our motivation, that we should come up with some method that should do true generalization, number one, and secondly, it should be able to handle the open set samples during testing. Remember, during training, I have labels for all the data in all the source domains, right? There is no notion of open set. I have only open samples during testing. Okay, so how on the fly the models can handle the unknown samples also, rather how we can generate some prompts additionally to take care of the open samples. Okay, so basically I want to learn prompt which is domain generic, number one, and secondly, it should be able to handle the open samples. So that's the motivation of this work. So any question till now?
There is one question in the chat
Yeah.
box. They can only write in the chat box, sir. They cannot unmute their mics, sir.
Okay. Let me just see that. Just a moment. What is the chat box? I cannot see the chat is okay. Chat, I can see that now. Okay, so it's domain calls now. So it's not self-supervised learning. It's different. Okay, as I mentioned that in self-supervised learning, the point is you have the data only, and from the data, the goal is to learn some meaningful feature that could be transferred to solve some downstream task. Okay, but here your point is you have multiple domains, all are labeled. You want to learn a classifier, and the classifier should be able to handle any new domain during testing. Okay, so that's the fundamental difference. Okay, so now let's move forward. So this is the motivation that we have till, of course, to come up with new prompting technique so that can handle any unaccounted domain shift between your source and target domains, and it should be able to any open set sample during testing properly out there. Okay, now in this regard, so basically I will talk about three of our works, which one of the first one came in 24 CVPR, where basically we kind of introduced the solution of this open domain generalization using prompting for the first time. Next, in this year, we extended the previous work where we wanted to see how does this model work, like if you reduce the number of training data, because annotating the training samples is costly, right? So basically, we want to have models that should work with less amount of training data. So that is the thing that we wanted to see. That's the Oslo prompt work. And in the other work, it's a disjoint work where we basically wanted to see that instead of telling all the target domain samples as unknown, a single class, can we basically cluster them into its different clusters based on the semantic similarity? Can we group them in different clusters out there? Okay, so that's the three things I'll just talk about. Okay, so now let's move to each of them again. So any question on the setup? I just want to make sure that all are in the same page. So maybe you can write if you have any question. Maybe you can take a minute to clarify if any question is there. So because if you have this idea clear, then the subsequent things will be easy for you to understand. Because my main plan is that I will give the overview so that basically nowadays whenever you have any model, you have to use it with Clip, because Clip really gives you pretty good performance. Okay. Okay, so if that is fine, let's move forward then. So these are the three works that I will talk about. So the first thing is the first problem of doing this prompt based way of open domain generation. Okay. So there are two aspects of the problem, as I mentioned. One is to come up with prompt which are basically what we call this domain agnostic. That's one part of the story, and the other part of the story says that we want our specialized prompt that should handle any open sample during testing. Okay. Now, So how do we handle open set or open sample? Because again, you remember that during training for all the classes, I have the labels, okay? But only during testing for the target domain, I may not have some label for such certain classes out there, okay? So that was the main point. So, I mean, a simple way of doing that. So I pass the target image. I just pass all the known prompt corresponding to the known classes. And if I find the similarity between them is less than a threshold, then I can say that, okay, this image does not belong to any of the known classes, so that I say it's an unknown, okay? Instead of cosine similarity, I can use any other distance, for example, or I can make a one class classifier, right? So where basically, it will just give me this distinction, whether it's a known class or an unknown class. So this all things are fine, but again, all depends upon definition of a proper threshold, right? And if you don't define the threshold, things will be bad. Now, another way of doing that is, can we define a prompt where the first context tokens, of course, will be learnable. In place of class token, I put the word unknown. Basically, I want a prompt for the unknown class. Now, the question immediately comes, how can I train this prompt? Because I don't have any image to define the unknown or the open set, right? So how I do, learn this specialized prompt to tackle the unknown class. Okay. Now, so this is basically the problem that I mentioned. So in the first solution, what we did basically, there are two parts again, as I mentioned, right? So there is one part where basically I tried to ensure that the learnable prompts are domain agnostic. So here what we do, I'm very quickly going through the idea. So I learned two kind of prompt. One is basically we call domain condition, the first one, and the other is called domain and class condition. Okay. Now I pass them through, and here this W's or V's, these are the learnable tokens. Okay, I pass them through the text encoder, and in the embedding space, I just make the subtraction of them. Okay, because one is domain and class, and the other is domain. If you subtract them, basically you get the class information, right? So this class information, I am just adding up with the image to get some latent visual image out there, right? So if you see this, this part of the figure, so I learned this to prompt, subtract them, get this semantic information, which is the class information. Somehow I include that information with the image, and I get this latent visual information. Okay. Now this DOM token is very specific. I'm because this is a domain token, right? So I'm not manually defining that, but I have a way where I actually capture this domain information directly from the visual property. You know, basically from the vision encoder, we did something. We basically took the output of the layer norm. There is some specific layer called layer norm. So the output of the layer norm has domain information. It actually captured the style information better. So basically, from the visual feature only directly from the visual backbone, I just get this domain token out there. Okay, so that's one part. Okay, so that's how we just ensure that the model handles domain agnostic information in the visual data, because that's why from the original images I just create the this latent visual space, okay, which is domain agnostic. Now the second part is how can I train the unknown class prompt. So here basically what I do, okay, so that was the first part. Okay, now let's do that. So I use diffusion to create some image which is potentially which does not belong to the known category. Okay, so what I do, I define two prompts. You know, I can use any of the this diffusion model. It could be instruct pix to pix, it could be GPT or any model, that doesn't matter. So I give them two prompt. I say them, give me an image of an unknown class, but that image should not belong to any of the known classes. That's it. Okay. So if we do that, then you find that the below one, this kind of open images like abstract image that does not belong to, the known categories, I get that images directly. So that's a very cheap thing, right? So what I do, I use another foundation model, and I just use this positive and negative prompting together. And I say that give me some image of unknown category, which should not belong to any of the known classes. That's it. So in this way, I just do this positive and negative prompting to generate this dopen, which is basically the training sample for the unknown class. And then the same thing, right? I just get I keep this prompt thing learnable, and I do the contrastive loss, all sort of stuff, and then finally train the prompts out there. And this model actually can handle any distribution, any domain of data clearly, and at the same time, it has a way to handle the unknown classes as well. Okay, so that's the ODG clip, the first method. So if you see result, this is quite interesting. Like we did experiment on all the standard multi-domain dataset, PAGS, VLCS, Officeome, all this thing. And I mean, the non-clip methods, for example, on an average, it has performance of around 60, 70% like that, okay, which is pretty less, of course, you can understand. When you start using clip backbone, the 60 went all up to 80s, okay? And then, of course, I have all the backbone, methods which are doing prompt learning. And they gave like around 84, 85, this much of performance. Now, the thing is that in our case, when we are actually trying to model this domain agnostic prompting, the performance go to almost 95%. So almost around 10% improvement we saw. And this H score is basically the average performance on the known and unknown class. So here also you can see that we got around 90% on an average, which means our model actually can handle the open samples in a much better way because we have a defined prompt and we synthesize some images to train this unknown prompt out there. Okay, so that's why this model really did well in both known class classification as well as detecting the unknown. So that was the first work. Now let's move to the second problem where basically we wanted to see that, I mean, since, okay, ODG clip was good, but it had this problem that, I mean, it has quite a lot parameters to train, okay? And it basically, it fails like if you have a small amount of data. For example, here I'm showing, like, I mean, if I have only one training example per class, this I mean, for example, this color is ODG clip, right? You can see that the performance is, it reduced to 60s basically, okay, 60s and 70s, which is pretty bad out there. So that was the motivation, like, can we do better? So that I again tried to solve this ODG problem, open domain generalization problem, but now I will have only 1 or 5 training example per class in the source domains, okay? And here we put a new model, propose a new model called Oslo prompt that actually solves this. Again, this is the, research gaps that we had. Okay. Exactly. We did this open domain generalization using prompting, right? So any other question? Yeah, so both domain generalization and detecting any open samples, during testing. So both the things are solved using that. So, okay, fine. So now coming to the next point. So now when I want to learn from a limited data, when I have extremely limited supervision, so then basically what happens, right? I mean, I cannot rely on the high level C, like similar to any other model like CNN, VIT and all. In CLEAP, it's also neural net, right? So it is implemented either using VIT or CNN, this kind of models only. But the point is that in CLEAP, since it is trained on this dual encoder, vision and text information together, so that's why it's semantically richer. Now, in all the previous cases, I mean, in this model, for example, for the visual feature, like what we considered was the final embedding from clip, right? So, I mean, you can assume that if it is VIT based clip, then you took the final CLS token. But the point is that, I mean, you cannot only rely on this final CLS token, which is a global high level feature for low shot kind of task out there, right? Because, I mean, that could overfit the model pretty quickly. So we need a representation which is much more what you call grounded. And by grounded, I mean is that can we go have a attribute based or part based representation for the task? So that was first thing, right? Can we have a better visual feature which is guided by the semantics of the part or the attribute information? Now, of course, I cannot just rely on this unimodal prompting. Need to do multimodal prompting because I need better synergy between the text encoder and the vision encoder. Okay. And finally, since I have again only 1 or 5 training example per class, now my pseudo open samples, the way I generated before, like using the positive and negative prompt, that should also be refined, right? Because I want really difficult pseudo open samples to generate so that, I mean, since, my feature space is sparse now, right? Because I have very few label data. So then my unlabeled data should, I mean, ideally should be close to the label data. Then only I can learn a, sharp separator between them. Now, given this challenge, I propose this model, this Oslo prompt. Now, first, let's see how, I refine my prompt for this pseudo open image generation. Okay. So now I use this prompt. So I put to GPT this thing. So, first I say that generate semantic category names which are closely related but visually different from the known classes. Okay. Previously, my idea was just give me some unknown class which should not be any of the known classes. That was the prompt. But now, first I'm generating some new class names which are different from the known class names, but they may be visually very similar. Okay. Next, what I do, I generate image for this new synthesized classes out there. Okay, so this is a two-step process. That is how I generate this pseudo open images, and this worked pretty well. So if you see, the left part of the story was the images that I generated using this ODG clip, the previous method, the previous prompting, and you can see that all the images are very abstract. But now, with Oslo prompt, like using this kind of prompting idea, I generate image which are much more diverse, and at the top I show the closed set classes out there, right? So you can see that now in Oslo prompt the generated images are much more closer in semantics to the closed set classes than what I had in Oslo prompt. Okay, so this is important because now I can really make a separator like open and close separator which is very sharp in nature, right? Fine. So that's one part of the story, how I generate better pseudo open samples. Next, for learning the domain, this prompt, basically, I use couple of new ideas. Okay, see, like for all the source domains, I know what is the class names, right? Uh, Okay, sorry. So I just want to, I know what is the domain names for the source domains, right? So basically what I can do, the prompts that I'm learning, basically I call it domain agnostic prompt. I distill the domain specific information to this. That's possible, right? Because any manual prompt has more specific information. So why not distill this information directly? It could be through some MSC loss or things like that when I'm learning the prompt. So this V1 to PM, these are learnable. At the same time, there is some loss function where I'm, kind of distilling the properties of this domain specific prompt into the domain agnostic prompt together. Okay. That's one part of the story. Second part is pretty interesting. Here, what I do for all the known classes, I just get the attributes. Okay, so again, I ask ChatGPT. So, can you give me 4 very distinguishable attributes per category out there? Okay, so once I get this attribute, then what I do, let's show from the figure, all the images that I have, right? So I am not using the CLS token of it. Okay, rather I am just projecting the CLS token in the space of the attribute through a cross attention, and then this new information that I am getting, which is attribute specific representation for the image, that is the one that I'm using. Okay, you can see that in the domain specific prompt for each domain image, I'm just adding this information. Okay, so basically I want to learn this domain agnostic prompt. What I do, I just do this alignment, which is basically inheriting the properties of the domain specific prompt out there. That's the only thing that I do. Okay. And with this modification, the model now actually can handle less data very well. Okay. So if you see again all the experiments, in one shot case in the top table, I take 1 training example per class. In the below table, I take 5 training example per class. So you can see all the other models has very, very poor accuracy in the 20s. Okay. So ODG clip did a little better, but still it's like suboptimal. Now Oslo prompt is actually beating ODG clip by pretty good almost by 10-12% out there. Okay, so basically the point here I want to make is that I have a model that can learn basically from one training example and can be generalized to new domains and can handle open samples also. Okay, so that's basically the type of model that I want in in different real world applications, right? So that's the second task of what we call Oslo prompt. And we have pretty detailed tabulations like how all these things they matter, how the loss functions matter. Maybe you can look into the paper and get more details about them, and for both of them I think the codes are available, so you can just try them out on your own. Fine. Now let's go to the third part of the problem, where what we want to ensure that I just don't want to group all the novel class samples in the target domain as one category. Rather, I want to see if I can cluster them properly out there. Okay, Now this GCD problem is very new. Okay, it came up in 22, 23 around that time. So the problem goes in this way. I mean, if you know semi-supervised learning, then you can correlate it better. So let's assume that I have a label dataset, a DL, where I have data as well as the class level. I have an unlabeled dataset DU xj, but here I can have samples from the known classes or some unknown classes. Okay. Now what is my goal? I want to learn a mapping so that any sample from this unlabeled set du should be classified to one of the known classes or should be clustered in a semantically coherent group out there. Okay, so I don't know how many clusters are there, how many unknown classes are there, but can I have a model that should be able to classify the known class sample in du properly and cluster the unknown class samples into semantically relevant groups out there. Okay. Now, previously we extended the problem in one of our 24 work where we wanted to ensure that what happens if DL and DU are two different domains. Okay, your DL could be color image and DU could be sketch for that matter. Okay. Now, just to clarify how this problem is different, you know DG, where I train on multiple source domain and I test on a novel target domain. Then I do ODG. So here basically on top of DG constraint in the target domain, there could be novel class data. Then there's a problem called novel class discovery, where basically I train on some known classes. And then my goal is to cluster some unknown classes only. And then comes a GCD problem where I jointly train on the label and unlabeled data. And my task is to cluster the unlabeled data to known as well as novel classes together. But you don't know how many novel classes are there. That's the restriction. Okay, so now in this setup, and this is very important problem, of course. Like, I mean, you can handle, the open set in a better way because, I mean, in the real world, for every model, there are many things which are unknown, right? So if we can group the unknowns properly based on similarity, then it will be easy to process them further, right? So that's exactly what we are doing, and it has many application in this medical imaging, autonomous surveillance, and all sort of stuff is out there. Again, so now, we propose this problem of what you call DGGCD, so domain generalized class discovery. So here, let's assume that in training, I have only this thing. Okay, I have a source domain labeled, and I say here, for example, you can assume that I have two classes, a guitar and the giraffe, and nothing else. This is what is available in training. Now during testing, I get a completely new domain where could be there could be samples from the known classes like guitar and giraffe could be there, but there could be sample from new classes also. And what do I want? I want to properly cluster sample from which is similar to each other, basically, right? I want to group them into 4 cluster, but I don't know how many novel classes that might be present. Okay, I don't have any idea about the novel classes. So that's the problem setup I want to do. It's a very challenging problem because first of all, how can we ensure that my feature space is domain agnostic, right? Because I have access to only one source domain only. Then how can I ensure that the feature space is discriminative, right? So that I can do proper clustering out there. And finally, I have to ensure that the model should be generalizable to new distribution. Okay, so the three things should be done together. So that's the idea. Okay. So again, so in the question, any question on the problem setup? Anybody, anything on the problem? Okay, so then for solution, I depend upon something called a meta learning based solution. Okay, so when I say meta learning, basically the idea is that I have a global model, then I define multiple tasks. I in every iteration I train the model on the task out there, and then I aggregate the information from the task to update my global model. In this way, as I train the model on multiple distribution of tasks, then I update the global model so that now the global model can handle multiple tasks. In our case, the task is basically multiple domain in a much better way. Okay, so that's the type of algorithm that we want, that we basically do. So again, in this case, it's not a clip-based model. So what I do, my model is basically a Dino, VIT Dino kind of model, because in these cases, VIT Dino is a standard model which is used out there. Okay. So I initialize this thing with VIT Dino. Now let's see every task model that we have, right? So in every task, basically, so again, what we have, I have access to only source domain, and what I want to do, I want to make the model generalizable across any domains out there, right? So then why not in every task, I just try to solve a separate this GCD problem, okay? And then I just get the property of the task feature, and then I aggregate the property of all the task feature, and this aggregated information is used to update the global model. Okay, so basically it tunes the parameter of the global model. So that's how it goes. Fine. So here we use a very popular concept which is called task vector. Okay, so let me just quickly define that. See, like I mean, this task vector idea came in 23. This is another very popular idea. So let's assume that you have a model, pre-trained model. Okay, and you just fine tune the model to classify cat and dog. You just fine tune the model separately to classify tiger and lion. Okay, so how can you update the model so that it equally can work well for both cat, dog, and tiger, lion? So what you do, you just take the feature difference, I mean the weight difference between, sorry, so let me define that. Yeah, you just find the weight difference between the pre-trained model and the fine-tuned model, right, for both the tasks. Okay, and let's call this thing to be a task vector. Okay, and then what you do in this case, you can define the task vector. So let's assume that my initial I mean there are two task vectors, this delta g1, delta g2, right? So this is basically the difference between your pre-trained model weight and the fine-tuned model weight. And if you just add this task vector, basically, so then you have a combined model that can work well for both the tasks out there. Okay, so that's a very simple idea. So it's called task arithmetic, and that's actually another way to fine tune a model, right? So you don't do or rather update a model. Okay, so you just fine tune the model on multiple tasks, create the task vector, which is the subtraction between the fine tuned weight and the pre-trained weight, and just add the task vector to the pre-trained model out there, right? In this way, you can simply do arithmetic and you can do many things out there. Okay, you should look into this because nowadays, I mean, majority of the cases in LLM we use the task arithmetic this process. So basically, I mean, the way we are updating the global model is through this task, arithmetic operation. Now, secondly, for each local model, each task model, what I'm going to do, I'm going to solve the GCD. For the source domain, of course, is the label part, and I generate some variation, like domain variation of the source domain, and that defines the unlabeled part out there. Okay, so for example, I use again the instruct pix to pix, and given the training domains, I just say that okay, add some rainy scene, snowy scene, this kind of stuff. That gives me different variation in the style. Okay, and then in each task model, I solve the GCD problem, which is basically fine tuning the model. And then I define the task vector, which is the weight difference between this fine tuned model and the initial model. I aggregate the task vectors and then I update the global model. In this way, I keep on doing for multiple iteration. So then basically my global model is now more powerful and can handle multiple domains or completely new domain in a better way. So this is exactly what we did. So that's a very simple thing, simple idea. Only you need to know this task arithmetic, and it's also simple subtraction, right? And then things can be done in a better way. So now, if you in the result, if you see, so I mean, all means what is the clustering performance in all the classes in target domain. Old means the clustering performance on the known classes. And new means the clustering performance on the new classes out there. Okay, we did a detailed benchmark, and you can see that the proposed method actually can do better than all the other baselines. So there's an upper bound, like I mean, if what happens if the target domain is available during training, right? Of course, it will be more, but other than that, you can see that this method actually is able to do good both in the old class as well as new class. So this is a case, as you can see there. I mean, for novel classes, you can actually go more into the novel class and you can cluster them in based on their semantic similarity. Okay, so that's the three thing. And of course, we have many ablations to show like how each of the model components, I mean, different backbones and all these things are performing here, right? And it's very interesting, like how this models they work. So basically, just to summarize again, I started with defining the problem of domain generalization. I mean, kind of motivating what is multi-domain learning, what is adaptation and generalization, and then I defined the notion of open domain generalization, and then I talked about like why nowadays it's more meaningful to deal with the foundation model, and what is CLEAP, what is manual prompting, what is prompt learning, what is unimodal versus multimodal prompting, all sort of thing. And then of course we had clear motivation that all these models, they actually are not good to handle this domain generalization setup, and particularly if there are new classes in the target domain during testing, they cannot handle that, right? So in ODG they basically fail. So that motivated us first to do the ODG clip, the first model, and then we found ODG clip is good, but it cannot handle limited supervision. Then we had Oslo prompt, where basically we wanted to see how you can make better pseudo open samples, or how you can make the visual feature more attribute oriented, right? So that helped. And finally, in the last work, we wanted to go inside the open set, and with this episodic kind of training, or this meta learning kind of way, we see like how we can make a model better generalizable to some unknown distribution, more discriminative, this kind of thing. So all these problems are very, very important problems. They have huge application in all the domains. And these are, I mean, because these are very new research endeavors, as you can understand. So there are many ways you can extend them, right? For example, you can just extend them with many modalities, right? Video, audio, and all this part, right? You can do a continual learning kind of scenario with that, okay? Or you can, enhance the quality of the open data that we are just synthesizing, right? So there are many ways we can just take these things forward. So now, of course, I mean, we found there are a couple of follow-up works from other groups where people are trying to use them in videos, right? They are trying to, improve the way we did prompting, those kind of things out there. So, I mean, finally, since these are now you have to do everything majorly with these VLMs, because they are much stronger and semantically much more superior. You have to do prompting. You have to do prompting better. So that's the only thing. Okay. And prompt learning is the solution, but even in prompt learning, this, how you handle different type of data, different distributions. Okay. So that's why, that is where the research lies in this case. Okay. And our work did some initial, thing in this direction, but of course there are many, many problems that are there, and hopefully we are also tackling some, and others will also tackle some. So finally, if you solve this thing, then you will have a wholesome, model that you can actually deploy in real world. Okay. Yeah. So I'll stop here. So any question if you have, I can take that.
Yeah, participants, if you're having any queries, please write it in the chat box.
Yeah. I think there is some question. Yeah. So basically, uh, the trade-off between model capacity and generalization is actually, see, like, I mean, CLEAP has been trained on, different type of data, right? What is more important is to come up with a prompt that actually can handle different domains. Okay. So CLEAP is already extremely strong, of course, very strong out there. But the question comes how you make the prompt stronger, okay? Because that's the main trade-off, right? So, I mean, we have a context length of M, for example. I mean, with limited context length using frozen clip, how we can ensure that the prompts are more generalizable. So that's where the trade-off is there. Secondly, can prompts be dynamically adjusted during inference? Oh, yeah, of course, it can be. So there is something called test time prompt tuning, okay? And in that case, basically the goal is that can we, given the target domain, unlabeled target domain, so can we, learn the prompt on the target domain directly, okay? And that is the notion of test time prompt tuning. So that is also a very popular way of research out there. So there are very recent method called OTPT. So you can just check that one. So that actually does that. So any other question?
Yeah, we can wait for sir 1 minute.
Sure,
Maybe
sure,
that
sure.
I think. Yeah,
Of course,
yeah,
of course.
yeah.
Yeah, yeah, yeah. how to learn semantics in case it are not arranged semantically in other type of models, like audio visual. See, like, I mean, nowadays a good way of getting the semantics is you can query the LLM, right? So, I mean, the models are available. They can give you really good, the semantic knowledge out there, right? So, for example, the way we did, right? We gave the class name and we wanted to get the attributes, right? Discriminative attributes, right? And then we use those attribute into learning this semantic features, right? So you have to come up with some module of that sort where you get the semantic information from this LLM, and then in your model you just try to encode it through cross attention, for example, the way we did, or some similar way. And semantic means, I mean, another way could be like you use some knowledge graph, right? Some common sense graph, all sort of this, large scale information, and probably you just pass it through a graph convolution network and use as a separate token. So that's also possible. Yeah. Is that clear? Okay.
Yeah. So thank you very much, sir, for your insightful talk on a very difficult subject and recent as well, because every reviewer is going to ask this kind of questions.
Yeah.
That where is the domain generalization performance of the model? So
Exactly.
probably
Yeah.
participants have got idea, at least the
Yeah, so
mathematical.
my main point was to, because what I've seen over the time, this is a very important, but this is something that, I mean, we may not always do, right, when we design a classifier or something, right? So that's why, I mean, the main point here is you just start thinking from this domain generalization point of view, right? Because these things are important. Okay, so if you want your model to work on real world, your model should be generalizable. Okay.
Yeah, absolutely correct, sir. I hope this idea, I mean, at least the participants have got this idea how important this topic is, although has been less explored, right?
Yeah,
So if you
exactly.
can
Yeah.
integrate all these concepts into your paper, maybe the paper, I mean, there'll be high chance of acceptance. I mean,
Yeah,
in
yeah, yeah.
journals
Because
also.
these are like, I mean, these are very active areas. I mean, people have understood
Absolutely.
now in the community. Yeah, yeah.
Absolutely. And Professor Biplab Banerjee is one of the active researchers who is currently focusing on this kind of actually work. So thank you
Thanks.
very much, sir, for connecting us, for
No,
joining
no, no.
us,
Thanks a
sharing
lot
your
for
valuable
having me. And it was
knowledge.
really nice, having this session.
Yeah. So I mean, in future, maybe if you will plan something in
Of
person,
course, of
we'll be
course.
happy to have you, sir.
Of course, of course. I'll also be happy to be there.
Yeah.
Okay.
Thank
Thanks a
you
lot.
very much,
Thanks a
sir.
lot.
Good
Yeah.
night, sir.
Good night.
Yeah. So yeah. I will request for the PPTs and all to all of the speakers. Some of them have shared, right? Very few, but we have videos at least, right? So that is for sure. I mean, YouTube videos, the links and all. So whenever it is required, you can go back and you can listen to them, right? So these are all very important things, right? Topics you can say. So although we have, in our schedule, although we have a lecture on diffusion models from 7:30 to 8:30, so actually this has been postponed to tomorrow.